Hi, I'm Professor Seth Chandler from the University of Houston Law Center, and this is the last in a four-part series on causal inference. It's for the course Analytic Methods for Lawyers. And in this video, we're going to look at 5 topics that really weren't covered in the prior 3 videos. They are sensitivity analysis. That is, what happens when we don't have the data on confounders? Can we still try to bound our estimates of the causal effect of various treatment variables? We're also going to look at 2 methods to resuscitate intractable causal analysis by adding nodes to the causal graph and edges, and we have data on the nodes. The first of these is called instrumental variables, and the second is called the front door adjustment. Finally, I'm going to look at 2 methodologies, and I feel a little like Monty Python here. I think that's 6 things we're going to look at that are used particularly in econometrics. Those are difference in differences and regression discontinuity. Here's the setting we're going to use to talk about sensitivity. We've got a causal graph here, and it's a very simple causal graph. We've got a treatment that produces an outcome y, but there's another variable u, unknown, that causes the treatment. It's related to what treatment you get, and it has an effect on the outcome. So one might think of this as the size of your kidney stone. This is whether you got fabled treatment A or B, which was the subject of the prior videos, and this is the outcome. And if you've been following the material thus far, you immediately know what to do. We have a causal path here, that's great, but we have a weak path graph here that doesn't have any colliders, therefore it needs to be blocked, and there's only one thing we can do to block it, and that's to control for u. All of which is great if you actually have data on u. But what if you don't have data on u? Well, let's see how bad the problem really is. Supposing we know the following about the data. We don't know what any individual's value of u is, but we do suspect that in general, the correlation between that unknown and the treatment is some value ut bounded between -1 and 1. We think that the correlation between u and y is some unknown value uy, also between -1 and 1. And we can measure the correlation between t and y, and we determine that it's 7/10. Now, these are conventional correlation matrices. We can, however, compute something called a first-order correlation matrix, which tells you the correlation between variables after the other variables are taken into account. And it's actually very much like multiple regression, where you're trying to come up with a coefficient in front of a variable after the other variables are taken into account. And so there's a glorious resource function, first-order correlation, which does this work for you, and it produces the same size matrix as your correlation matrix. It's a ghastly thing. I just want to look at the correlation between t and y. Okay, so here it is, second row, third column, and okay, so let's just run this again. I forgot to run it, and now I think this is going to work splendidly. Yes. All right, so it's some horrifying expression in ut and uy, but what we're interested in is where might that expression have a value that's actually less than 0.2. That is, before we took the confounder into account, we thought the correlation between treatment and y was 7/10. And what I'm curious about is what values would ut and uy have to take on before we really experienced a pretty massive change in that correlation down to something that's less than 0.2. And I'm going to use the Wolfram language function region plot to find the areas in which this expression is true. And we'll run that now. And there it is. And you can see really it's pretty difficult to get a value of the correlation between t and y after u is taken into account that's really quite small. And so even though our value of 0.7 might not be correct because there is a confounder, on the other hand, it's unlikely, for example, that the confounder is going to make the relationship negative. And in fact, what we can do is we can produce a lovely contour plot showing for different combinations of ut and uy. And what should the professor do? The professor should label his axes. I'm back. All right, I fixed the axes. Had a weird error message, which I think is due to a change in the version of Wolfram language. And now this should just work. We're going to get contours of the value of the correlation after the confounder is taken into account. And you can see, by the way, that if ut and uy are 0, then there's no confounding and our correlation is as it was. You can also see that under some circumstances, some combinations of ut and uy, you might get a correlation after confounding was taken into account of 0.9. You could also, as we've noticed, go down to 0.2, or even in some very rare circumstances, get a negative correlation. But this kind of tells you what it would take in order for the unknown variables to severely perturb the correlation that we found without the ability to know the confounding variables data. All right, and you can see we can do a little more math here to show what values would the correlation between t and y take on after the unknown was taken into account for different ranges of values of ut and different ranges of values of uy. And you can see that, yeah, it would affect it, but not hugely so. In fact, what this code is doing is it's sort of creating a box here for the permissible values of ut and uy. And if we go up to our contour plot, we're basically saying what's the highest point on the mountain here, whose contours we see within that box. And so, although confounding is important, before you panic that you don't have data on all the possible confounders, you ought to realize that it might not ultimately have that great an effect. Okay, and that is sensitivity analysis. Now, I will tell you, I made life very easy for myself here because I picked a very simple causal graph. This is about as simple as it gets. To do sensitivity analysis when we have graphs of the complexity that we've seen in this course is considerably more difficult, probably requires experimentation, sort of synthetic data, rather than some sort of formula like this. But it can be done, and again, before you panic because you don't have every piece of data you would like, just recognize it might not make all that much difference. Next topic, instrumental variables. Okay, so we just saw how sensitivity analysis could give you an idea of how big the problem from the absence of data is likely to be on your ability to determine the effect of some treatment on the outcome. But it doesn't actually do anything to solve the problem, it just lets you know how big the problem is. There's a solution that can sometimes be used, and it's called instrumental variables. The idea of an instrument is you find for every person, or what your unit of observation is, or your study unit is, to use the jargon of causal inference, you find a variable that correlates pretty well with the treatment, but which you're confident does not correlate with the outcome. So it's not a confounder. And then, instead of using the actual treatment to predict the outcome, which might be confounded, you use the treatment value predicted by the instrumental variable. And your predictions may be worse than if you didn't use the instrument, but you won't bungle the computation of a causal effect by having confounders. What I'm going to do now is I'm going to give you a classic example. And the fact that it is classic is, to me, evidence that finding an instrumental variable is often very difficult. But sometimes it can happen. Supposing we want to determine the effect of years of schooling on lifetime earning, and we want to do it causally. That is, we want to know, okay, supposing we required an additional year of schooling, supposing we increased the penalties for truancy. To do that, we need a causal graph, because years of schooling, yes, it probably does affect earnings, you should all hope so, but academic ability might be affecting both how long you're willing to stay in school and your earnings after the fact. And so if you don't control for academic ability, you're not going to know whether the association between years of schooling and earnings is causal or whether it's simply confounded by academic ability. So here's what we do. Here's our graph. Okay, we have ability. It affects years of schooling because perhaps people with more ability don't get frustrated in school, so they stay in it longer. Schooling does affect earnings because there's your nice, beautiful piece of sheepskin, but also something that affects earnings is your ability, which manifests, your employer can presumably see. So here's our school graph. Okay. The problem we have is, this is easy to measure. This might be easy to measure, but ability might be something that it's tough to figure out what to do, because otherwise we've got a backdoor path here that we can't block because we don't have the data. All right. Here's the idea. We're going to figure out how long people stay in school based on their proximity to the school. Maybe we have data on that. And then we'll use, instead of using actual schooling to predict earnings, we'll use predicted schooling, which won't be confounded. Now, there's going to be noise in our data because predicted schooling is not the same as actual schooling. Presumably, our predictor isn't perfect. But the noise won't be biased or correlated with other causal agents such as ability. At least that's our hypothesis. Okay? So what we've done, just as in a randomized controlled trial, is to break any causal relationship between ability and schooling. Ability is still a confounder, but it won't bias our estimates. And so to do this, we don't have to do a randomized control trial. We just have to go back and get data on the proximity to school for each person about whom we know earnings. All right, so what we're going to do is sometimes called mutilating the causal graph. We're going to delete schooling. We're going to add predicted schooling and proximity, and then say that predicted schooling causes earnings. So here's our instrument graph, and you can see that there's no confounding. Ability does not affect predicted schooling, and ability does not affect proximity. If it did affect proximity, then we've got a faulty instrument. All right, if you want to read about D-separation and its relation to all this, be my guest. But let's get some data here. This is synthetic data. And so what we have is, we have proximity, we have schooling, there's a secret column here called ability, but we can't know that, and we have people's lifetime earnings. Okay, so what I'm going to show you is now sometimes called two-stage least squares. If you hear things like endogenous regressor, you know you might be in the econometrics world and two-stage least squares. But this is not hard, really. Okay, you know how to do this. You just do a linear regression. Yes, you could do machine learning if you felt motivated, of proximity on schooling. So let's do that here. And we come up with a model that says that every proximity unit, whatever that is, adds 7.7 years to our estimate of schooling. And we can see, is this a decent fit or not? And I'm going to run a parameter table, and I'm also going to get that old F statistic. All right, so what do we see? We certainly see that proximity has an infinitesimal p-value. When we look at the F statistics p-value, we see it's the same thing, by the way, as the proximity p-value, and it's 418, okay? The rule of thumb is, in order for this instrumental variables thing to work, you want the F statistic to be bigger than 10. So for example, supposing instead of trying to predict years of schooling using proximity to the school, I used ice cream flavor preference. Now, could ice cream flavor preference be correlated with years of schooling? Sure. Maybe people who have the good sense to like chocolate more stay longer in school. But odds are that's not the case. And so, yeah, it's true that ability is not it does not cause ice cream preference, at least hypothetically, but ice cream flavor isn't going to predict schooling very well, and so ice cream flavor would be a cruddy instrument. So the search, and there's like a whole field of academia devoted to finding instruments, is to find something that predicts the treatment well, but isn't caused by anything that also predicts and causes the treatment either. All right. With that, here's what we can now do. And here, by the way, here's a plot showing you, again, that we have a pretty good fit here between actual schooling and predicted schooling. Okay, so now what we're going to do is we're going to fiddle with our data set and add a column predicted schooling, which you can see, by the way, is pretty close to real schooling. All right, we're done with that. And now all we have to do is regress earnings on predicted schooling to get an unbiased causal estimate. Here we go. All right, and it turns out that every year of schooling causes, regardless of ability, a $127,000 lifetime increase in earnings. We ought to look as to whether we've got a decent R squared, and we certainly do. So, that is how you use instrumental variables. Now I want to talk about some cautions. Here's one caution. Let's look at this graph. Supposing, yeah, proximity can predict predicted schooling and predicted schooling can predict earnings, but supposing that both proximity and earnings are affected causally by the wealth of your family. Maybe richer families live closer to or farther from the school, and probably richer families, the kid has richer, wealthier earnings. In this case, proximity is no longer a valid instrument because there's a backdoor path. There are ways, advanced ways of dealing with this issue, but for now I want you to see it as a yellow flag. Okay, so far in our discussions of causal inference, we've spent a lot of time on blocking non-causal paths. And those non-causal paths, you'll recall, require you to go backwards on an edge. And so they're often called backdoor adjustments. Now I want to talk about the front door adjustment. It's a lot of fun, and it's somewhat similar to instrumental variables. The idea, again, is to tinker with the causal graph, find something you can measure, and then do things in steps to deduce causation. Let's look at our causal graph again. And you remember the fundamental problem is U is a confounder. U causes both the treatment and the outcome, and the way we should deal with this and do calculus is to run a regression in which we include U as one of our independent variables and have a basis function with U in it. But that doesn't work where we don't have data on U. Okay, so here's what we could do. Supposing, I'm going to show you a slight modification of the causal graph. Supposing the treatment doesn't really cause the outcome, the treatment causes some mediating variable, and it's that mediating variable that causes the outcome. Now we actually can estimate the causal effect of T without having data on U. Here's how we do it. Okay, first step is to estimate the effect of treatment on the mediating variable. We don't need to block any backdoor causal path because Y is, drum roll, a collider. So it's already blocked, and therefore the fact that we don't know U is irrelevant. So we can determine the causal effect of T on M. We can also compute the causal effect of M on Y. Why is that? Because yes, there's a backdoor path, and yes, there are no colliders, but what could we use to block this backdoor path? We could use T. We can figure out the effect of M on Y controlling for T on which we do have data. And we then have two functions. We have a causal function of T on M and a causal function of M on Y, and we can simply then compose those two functions to get the effect of T on Y. Who was smart enough to figure that out? Our good friend Judea Pearl, who came up with the idea of the front door adjustment. All right, let's see it in action, although really, you've got the concept now. All right, here's our data, T, M, Y. I'm not showing you U because we don't know U. All right, so first step, let's do a regression of M on T. We'll do that. This should be old hat for you now. Here's our function, f1. I've written it as a pure function because that's going to make it easier to compose. Now, let's clear the variable M. It's a nuisance. Let's regress M on Y, but controlling for T. And that's going to give us F2. And now we just compute what is F2 of F1 of T, which is M, and T. Okay? That's, remember, F2 wants two variables. It wants a variable for M, and it wants a variable for a value for T, a value for M and a value for T. And we're going to give it the value of M here, and we're going to give it the value of T here, and if you do that, and you expand it out, this is the unbiased effect of T on Y. Every increase in the value of T causes a decrease of 0.371 on Y. Next method of causal inference, and it's one that is used very frequently in econometrics. It's called difference in differences. And I'm going to teach it to you using the classic example. Here's what we are interested in. Apparently, somebody installed a large, obnoxious public incinerator in some neighborhood. And what we're interested in is what causal effect did the installation of that incinerator have on home prices? So apparently home prices were first measured in 1978. This gives you an idea of the time at which this methodology is developing. And at that time, apparently nobody anticipated that this horrible incinerator was going to be built nearby. And in 1981, they measured house prices again. We have other data on the homes that didn't change between 1978 presumably, such as its square footage, how old it was when it was built, and things like that. So what we're trying to do is to separate out the effect of the incinerator from the effect of changes in the overall housing market. And by the way, this was a period of very, very high inflation. All right, so let's go get the incinerator data. All right, here's our data. There's actually a lot of data that's sort of off to the right here that you can't see, but we have a lot of information on the data, including when the price, for example, was being measured. If you want to know what each of the columns means, I've included a little table in the notebook. All right, the authors of this study assumed a causal graph. I'm going to show you what that is in summary form. It's whether the home was near the incinerator, other covariates about the home, like how many square feet it is, and whether the measurement is taken in 1981 after the horrible incinerator had revealed itself. Okay, so we don't need anything fancy to know what to do here. We can regress price on any of these variables, any combination of these variables, and we don't have to worry about confounding because there's no relationship going between any of these other variables. So let's actually look at a linear model fit where we're predicting the price of the house based on whether it's near the incinerator and whether the measurement is taken in 1981 or not. All right, and if we do that, it appears as if being near the incinerator dropped the value of the home by $23,896, which, given that this is sort of the median price of the home in the area back in 1978, yes, that's what you could buy a home for, it's a big deal. All right, and we can look at, is this model any good? We've got p-values that are great. Our regression isn't doing so well, although it's not terrible. But what I just did wasn't really very good. And by the way, you can see the residuals don't look right. And that's because being near the incinerator kind of has a different meaning in 1978 than it does in 1981. In 1978, it just means what block you're on. But in 1981, it means whether the soot and smell from the incinerator is coming over your home. And so really, we need an improved causal graph. Yes, there are covariates, the square footage, which isn't affected by the whole incinerator business. But what we kind of need is a variable that captures the combination of being near the incinerator and it being 1981. Being 1981 is still important because there was inflation and changes in the housing market. Being near the incinerator might matter because maybe it's a nice neighborhood or a not nice neighborhood. I suspect the latter. But we need this combination in order to make it work. And by the way, I'm using the language of causal graphs. The people who invented difference and differences did not have that luxury. But since you know I like causal graphs, I'm going to be using it here. All right. So if we want to predict the effect of it being 1981 and near the incinerator, you can immediately see what we need to include in a valid adjustment set. We've got a backdoor path here. The only thing we can block is being near the incinerator. We've got a backdoor path here, so we need to block whether it's 1981. And adding covariates is harmless, and it might increase the accuracy of our prediction. So here's our linear model fit that we can use. And we can now get our new parameter table and we can see that a better estimate of the causal effect is it dropped the price by $11,800. That's still a lot of money, but not quite the same amount of money as we saw before. Is our estimate much better? It's a little bit better, but not really way better. We can also see the effect of inflation here on housing prices. And we can also see apparently that being near the incinerator was always a bad thing. If you've looked at any of the material on environmental justice, you will see that environmental nuisances tend to be located in poorer neighborhoods, and often there's a racial component to it as well. All right, there's some additional subtleties in the notebook which I am going to gloss over because I want to get to difference and differences kind of the way it's done without a causal graph. And here's the idea. We're going to take our data set and we're going to group it by whether you're near the incinerator and then whether we're measuring it after the incinerator is installed or before the incinerator is installed. And then we're going to look at the mean of the prices. And by the way, if this sounds a lot like potential outcomes to you, that is no accident. So there's our query and that we're going to construct, and let's run it on our incinerator data. And what you can see is that if you lived close to the incinerator, your house price went up by roughly $7,000, but if you lived far away from the incinerator, your house price went up by $18,790. So these are the differences, and so what do we compute with difference in differences methodology? We compute the difference in the differences. So 18,790 minus 6926 is $11,863.90, and that is the difference in differences measure. By the way, those of you with photographic memories are going to think, where have I seen $11,863.90 before? And if we go back here to our regression, where we regress price on whether you're near the incinerator, whether it's 1981, and the combination of the two, look at that coefficient in front of the combination of being near the incinerator and it being 1981. Same thing. That's no coincidence. These two methodologies are essentially equivalent. One other point. One of the reasons the earlier regression didn't do very well is that the problem we're looking at is essentially nonlinear. It's not being near the incinerator that matters. It does, but it's not the only thing that matters. It's not that it's 1981 that matters only. It does, but not exclusively. It's the combination of the two things that matters, that really drives the value of your house. And so back in the day when this methodology was invented, they didn't have easy methods for dealing with sort of nonlinear systems like this. And today we do. We have this thing called supervised machine learning where it looks for what is a sensible nonlinear relationship between things. And so my own thought is difference in differences has the virtue of being somewhat simple, but today I would suggest that it's probably better to just use supervised machine learning. Into the home stretch, regression discontinuity. It's actually been around for a long time, but it's sort of had a resurgence as people realize its relationship to causal graphs. And there's a specific scenario where regression discontinuity is very useful. The idea is you have some cutoff score, and people below the cutoff are treated one way, and people above the cutoff are treated another. But the cutoff is somewhat arbitrary, and therefore if you look at people who are close to the cutoff, they should be kind of similar to each other. And therefore we can see whether being above some cutoff where you got some treatment or being below the cutoff where you didn't makes a difference. And obviously it could work the other way, where you got the treatment if you were below the cutoff and you didn't if you were above the cutoff. All right, so I'm going to give you an easy to understand example for law students. Supposing the law school assigns students to a special bar preparation class based on whether their law school GPA is below some threshold. So Participation in the prep class is the treatment, okay? And what we're trying to predict is whether someone is going to pass the bar exam, okay? So I'm going to posit that there's stuff other than your GPA that affects whether you're going to pass the bar exam. Maybe that's your intelligence or your family situation or your diligence or your grit or your course selection or whether you had a nice bar examiner or not. But the idea is you've got stuff that affects bar passage. You've got stuff that same stuff probably affects your law school GPA. And then your GPA affects whether you are enrolled in this prep course, and maybe being enrolled in this prep course affects the probability that you're going to pass the bar exam. Remember, a causal graph doesn't mean that there is a causal relationship. It's the absence of an edge that means that there isn't a relationship. All right, so we're back to our fundamental problem of causal inference. That is, we can't have law students who are both enrolled and not enrolled in this prep class, and we can't have multiple bar exams. But here's what we can do. We can find the people in the prep class who have the highest GPA, the people who are closest to the cutoff. And we can find the people who aren't in the prep class with the lowest GPA. And the theory is that those people on average should be fairly similar in their stuff. And therefore, if we see, for example, that people who took the prep class in this grouping of sort of people right on the borderline is higher than it otherwise would be, that's an indication that, in fact, enrollment in the prep class is having a causal effects. All right, so let's take some synthetic data. I actually used data for the University of Houston Law Center for this, not any individual student data, just aggregate data. All right, so we get a function that tells you what your class rank is based on your GPA. So in order to be in the top 5%, apparently you needed a class GPA of 3.83, pretty terrifying. And in order to be in the bottom 10%, even a 2.891 puts you in the bottom 10%, thanks to great inflation. All right, so we're going to create our class of 1,000 students. I'm going to give them a stuff value, a class rank, and a GPA. But of course, we don't see the stuff value. If we saw the stuff value, we wouldn't need regression discontinuity. We just see, hey, what's their GPA? And we'll ultimately see, we'll know whether they were enrolled forcibly in the bar prep class, and we'll know what their, how they scored on the bar. All right, so let's run this. And for the moment, by the way, we don't have the bar score in here. All right. Now, let's say that we're going to enroll the bottom 10% of students in this bar prep class. All right, and so now we're going to have a more complete data set in which we have hidden stuff. We can't see that. We do know their class rank. We know their GPA. We know whether they were enrolled in the prep class. So this individual who had a 2.728 GPA was in the bottom 1.5% of their class. Yes, they were put into the prep class. And we have their bar score. Okay, so we can make a plot now of GPA against bar score. We do that. Here's the plot. And to the eye, maybe we can see something, maybe. Best fit line to the left of the cut is like that, and maybe to the right it's like that. Hard to see, and that's why we have to do regression discontinuity analysis. So what I want to do is to get people who are close to this cutoff value. That is, I don't want to compare, someone with a 3.8 GPA to someone with a 2.2 GPA. Rather, I want to look at only these people on the thought that probably their stuff values are roughly the same, and it's only because of sort of an arbitrary decision to set it at 2.9 that they were assigned or not assigned to the bar class. All right. So there's one other thing to do, which is you kind of want to weight people who are really close to the edge, to the border, more heavily than people who are farther away. And that's what this little bell and whistle does. I don't think you should obsess about the bell and whistle. But the idea here, let's look at this code. First, pick people whose GPA is close to the border. Then run your typical linear model fit where we're looking not the basis functions, or let me just say, all we're looking at is their GPA and their bar score. But our basis functions are what their GPA is relative to the cut, that 2.9 cut, whether they were below the cut and therefore were enrolled in the GPA. And then the other thing we're going to do is we're going to weight each case based on how close they were to the border, where people who are really close to the border get weighted more. And when we run this, here's what we find. We find that for, this is the variable that is looking at were you enrolled in the course, was your GPA lower than 2.891, and it's suggesting that in fact it increased your bar score by 18.99 points. We've got a good p-value. On the other hand, our model isn't great. So that's a pretty good use of regression discontinuity analysis. Now, the question is that real? What if I looked at people who were close to 3.2? Maybe even though there was no decision that was based on that, maybe I'd see the same kind of discontinuity. Maybe this is just an artifact. And so one of the things that we can do is to pick a different cut score. And so let's pick 2.99 and see if what we start to get. And it turns out that now our p-value is 0.58, and we can no longer be certain that there's any difference between people at 2.989 and people at 2.992. So it looks like our regression discontinuity analysis was real. I want to do one more test. I'm going to make some more fake data while I'm at it. And this fake data, being enrolled in the bar prep class, has no effect at all. Okay, so I'm constructing it so that being stuck in the prep class doesn't affect your bar score. And the question is, are we going to get a false positive? Is our regression discontinuity analysis going to nonetheless say, oh yes, being enrolled in the bar class matters? All right, so we're going to run our code here. We'll look at the parameter table, and we're going to see that when being enrolled in the bar prep class has no effect, our regression discontinuity analysis gets a very high p-value. And so this is suggesting that regression discontinuity analysis really does work. The conditions you need are for assignment to treatment or not based on a cutoff. There are fancy methods of regression discontinuity analysis that kind of look at what if it's a soft cutoff. But regression discontinuity for us involves hard cutoffs and assignments on that basis. Well, we are done with our study of causal inference through our 4-part videos. And if you're watching this for the 2022 fall version of Analytic Methods for Lawyers, you're going to be very excited to know that this is the last video for the course. It's been quite a journey, and I hope you pat yourself on the back, not only for having listened to my voice and videos for over 30 hours, but also for having on the way learned a huge amount. Just look at what you've learned. You've learned to program, you've learned statistics, you've learned about statistical power, p-values, p-hacking, you've learned how to use the query language in Wolfram language, Bayesian statistics, Bayesian regression, chi-square tests, And then if that wasn't enough, we did machine learning, and you learned about bias and variance and all those statistics of the confusion matrix, various methods of supervised learning, including symbolic regression through our guest lecture. You've learned how to construct a neural network and train it. You've learned about discrimination, how you can make art with machine learning, and finally, in these last set of videos, you've learned about causal inference. My hope and belief is that this is only the beginning of a journey. I believe you're going to see and use much of what you've learned in the years to come. Just think of what's happened in the world in the past 10, 15 years in terms of all the material that we've covered here today. That pace of progress is unlikely to change. You have a major head start in it, and when you see issues in your firm or your life which seem to involve some of these issues, I want you to grab them. I want you to use them, and I want you to give me an email or a call and let me know what you've been up to. Thanks so much. See ya.